Hello everyone, welcome back to my tutorial. In this tutorial, we are going to see how to solve this thermostructural analysis of pressure vessel using salome. So continuously I am putting FEA problems using salome in my channel. Please don't forget to subscribe my channel and click the bell button for notification. Now we'll see how to solve this pressure vessel problem in salome. So this is the material property I have taken. I have taken a steel material property. Boundary conditions. Inside surface temperature is 415 Kelvin, as well as inside pressure is there, which is 3 megapascal, and external there is a convection with the external temperature of 293 Kelvin and heat transfer coefficient is 25 watt per meter Kelvin. In structural, we have inside pressure of 3 megapascal and this bottom faces are fixed in all the directions. In thermomechanical analysis, what way we are going to solve is, first it will solve thermal analysis, then the result data will be imposed to the structural analysis model and it will apply the structural analysis boundary conditions and loads and it will calculate the thermal stress. Now we'll model this case using salome. First I have opened salome. First we'll move into geometry model. This pressure vessel I have already modeled using geometry creation tools. Now I am going to directly import the geometry using import option. Go to import step. So this is my file. So this step file I am going to open it by using salome geometry model. Just choose this pressure vessel step file, just open it. So now we just want to model it in meter. So this geometry is created in mm. That's why this is showing this warning. Just give yes. So this is my model. After importing any model, check the dimension of the model by using inspection, dimension, bounding box. The maximum distance in x direction is 1 meter. The same dimension it is showing. Now the dimension is correct. Now we'll create a groups to apply the boundary conditions. We have two groups required. One is inside surface, another one is external surface. That is for temperature problem. For structural problem, we need inside surface, which is we used to create in thermal problem. The same boundary condition we can use. Then we have to fix it these two surfaces. Now we'll create a inside surface group. For that, just select this model 1, go to new entity, groups, create groups. First we have to create face group. To select the inside surface, we need to hide the external surface. For that, just select these external surfaces by pressing the shift and hold it. Now just continuously select the external surfaces. Here also these two surfaces, similarly this surface as well as this surface. All the external surface I have selected, just hide selected. So here you can see this is I forgot to select, just hide it. Now all the external surface I have added. Now we just want to select the inside surface. Just select. Just add it here. These two surfaces also we need to include. Just add. Just add. Here also there is a 4 surfaces. Just add it here. That's it. Now this is the inside surface. This is, I'm just saying, inside. Any name we can give for easy understanding. Inside surface. Just apply. Then you just give show all, select, show all the subsurface. Next we need to select the outside surfaces. For that just select all the surfaces. Then remove the inside surfaces. See here, only the inside surface number only selected. Just remove it. Then we have to remove this surface as well as this surface. Just remove it. That's it. This is external convection. External convection. Here you can see, for applying the inside surface temperature as well as pressure, we have created one group. That is enough. Then to apply the external convection, we have created the group. Then to apply the fixed boundary condition, we have to create one group. So for that, show all the subsurfaces. Select this face, press the shift and hold, select this face. Just add it here. Here we have to fix it. Fixed X, Y, Z. That's it. Now we have created all the groups. Now we'll check the groups. This group is correct. This is the external group. Here you can see only the external surface is showing. Now this is also correct. Then again select this one. This is the inside surface. Now everything is correct. Now we'll save this file. Then save it. Now we can create the mesh by using a mesh model. Just go to mesh. Select this model one. Select this mesh. Create mesh. Here I am going to use tetra element. I'm going to use NetGen algorithm. NetGen 1D, 2D, 3D. Simple parameter. Fine mesh. Just save OK. Apply and close. Just compute it. We can go for very fine mesh also. Initially start meshing with the coarse mesh. Then make it fine. This mesh is enough for me for a study case. For real case, we just want to make little finer mesh. So now I have created the mesh. Here we can check the groups also taken into the mesh. So while naming the group names, we have to avoid space. So instead of space, here you can see I have used underscore. Now we can go for aster study to create the setup. Just go to aster study. Just save OK. Here we can use the assistant to create the thermomechanical analysis case. Just say next. Next. So thermal conductivity is 45. Young's modulus is same. Poisson ratio is same. Thermal expansion is 12 e power minus 6. This is not required. Just keep it 0. Go to next. First one is imposed temperature groups. So inside, here you can see inside temperature is 415 Kelvin. Inside surface 415. Just next. There is no heat flux. Give no. select next. There is no volumetric heat source also, select next. Here you can see we are not applied this boundary condition, because this boundary condition we cannot able to apply using this assistant. After that we can modify it, then we can do it. The initial temperature also it's required only for transient problem, so this also we should take it out. So initially you just give this value. There is no time discretion not required, because we have to solve by using a static analysis, steady state thermal. Now we are moved into mechanical boundary conditions, imposed degree of freedom on the groups. So we have to fix all the fixed groups, 0, 0 and 0. Then is there any pressure? Yes. In this inside surface we have to apply the pressure of 3 megapascal, that means 3 e power 6. Then we can save this file. Just naming it as result.rmed. Just save it. Just finish. Now we have created the setup. It's not the correct one. We have to modify the setup. So first we are reading the mesh is correct. Then we are defining the thermal analysis model. Again we are defining the mechanical model. Similarly we are defining the material property for thermal as well as mechanical. Here rho Cp is not required. Remove the rho Cp. Just edit, remove, just save OK, just apply. Here you can see rho Cp is removed, save OK. Now we are assigning the material to the model. Then this list ER is not necessary, just delete this one. Then load step, first one is inside temperature. Then convection boundary condition is not created, so just add it here using the exchange, edit, element group, external convection, just save OK. Here see the boundary values. The reference temperature or external temperature is 293 and external heat transfer coefficient is 25. External temperature is 293, heat transfer coefficient is 25. Just save OK, just apply and OK. Now we have applied both external convection boundary condition as well as inside temperature. Then mechanical, the bottom surface we are fixing it. Similarly inside we are applying the pressure. Just go to the thermal solver. This is the thermal solver. Here initial temperature is not required, time step also not required, because we are going to solve it as a steady state thermal analysis, linear thermal analysis. Just apply OK. So in material for the mechanical analysis, here we have to apply reference value. This is very important, 293 Kelvin, and we have to impose the thermal value to the model. This transient, this is the thermal solver data. Just save OK, apply and OK. Then mechanical solver, this time step is not necessary, and we have two boundary conditions. This is both are required. Just apply and OK. Then output, we have to take thermal output as well as the mechanical output. This mechanical solver only it will calculate the displacement. To view the stress values, just go to post processing, call champ, use this automatic, renaming it. Here just choose mechanical, both we have to tick it, sigma LNO and sigma nodal, SAEQ LNO, SAEQ nodal. Just apply and OK. Now we have created this ratio meca. The same value has to be taken into the output. Instead of meca static, we have to choose call champ. Here tau champ make it as. Just say OK. Just apply and OK. Now we have defined everything. First it will solve the thermal analysis. But first it will apply inside temperature as well as the external convection. It will do the thermal analysis. Then it will take the temperature data into the mechanical solver. Then it will do the mechanical analysis, structure analysis. So now we'll solve this case. 5 seconds. I'm just giving more memory. Just run it. Before that, it is asking us to save this file. Just save it. Just run the case. Just wait for a while to solve this model. If any error comes, it will show in this window. From that, we have to modify it based on the error. Now it is solved without any error. Here you can see it is solved thermal analysis as well as structural analysis in a single stroke. Here you can see all the files are taken, memory, everything it is showing. Now we'll go for a paraview to do the post processing. Just right click this built-in, then open it. Pictures, code aster. So this is my result file. Just open it, then apply it. Now you can see here itself there is a temperature data as well as the structural data. First we will see the temperature results. So this is the temperature profile for this model. So 400 Kelvin is the minimum temperature and maximum temperature is 420 Kelvin. Now we'll see the stress data. First one is displacement. This is the displacement value. So maximum displacement is 7.6 e power minus 4. This is the x value, y value, z value. Now just go to here we can modify this by changing the value into blue to red rainbow, and here we just modify it into 12 number of values. So this one is the z displacement, and this one is the y displacement, and this one is the x displacement. And we can see the directional stress also. I'm just changing this into also in same rainbow, blue to red. Then just apply and close. This data I'm just making into 12. This also I'm just keeping here. This one is the magnitude actually. This is the x display x. So maximum x is getting 110 megapascal and compressive stress is 600 megapascal. This one is the tensile stress and this one is the compressive stress. Similarly, sigma yy, this one is sigma yy stress pattern. Similarly, sigma zz. To see the shear stresses, sigma xy, sigma xz, sigma yz. 3 shear stresses. Now we can see the von Mises stress. Just go to SIEQ node. This one is the magnitude actually. I'm just changing this value into blue to red color. Just blue to red rainbow. Just apply and close. This one is the magnitude. Now we just want to see the von Mises. So the maximum von Mises stress is coming around here of 300 megapascal. Here stress is very high, around 530 megapascal we are getting. That is because we are fixing completely here. The stress is very less, around 1 megapascal in this closed ends. Here stress is very high, that is because of thermal expansion, which is via restriction we are giving it. Here one meter signed also we can see. So compressive stress will not make. So this one is a 1 meter strain. So in this tutorial we have learned how to solve thermomechanical analysis of a pressure vessel using salome. In next tutorial we will see in the different case. Please subscribe my channel for more videos. Thank you.